All right, we're going to conclude section 12.5 in this video. We're going to continue with some exercises. So we're on page 794. We are doing number 14, which says, in exercises 11 through 15, find the tangential and normal components a sub t and a sub n of acceleration. And they give us that our vector function is r of t equals a vector whose first component is 4/5 cosine t. The second component is 1 minus sine t. And the third component is negative 3/5 cosine t. All right, and we want to find the tangential component of acceleration and the normal component of acceleration. So first, let's just write down those formulas again. So the tangential component of acceleration, two different formulas. We can either take the derivative with respect to t of the magnitude of velocity, or we can do velocity dotted with acceleration divided by the magnitude of velocity. So we can do either one of those. For the normal component of acceleration, we have two options. We can do the square root of the norm of the norm of acceleration squared minus our tangential component of acceleration squared, or we can do the magnitude of v cross a over the magnitude of v. So now we have all of these, all four of the things in front of us. We're going to use whichever one seems like it's going to turn out the easiest once we start doing some computation. So you always want to do the tangential component of acceleration first, just because you could use that in finding the normal component. And both of them would require the magnitude of v is required for that one, which could, if you go this route, you already have what you need for that as well. So let's always just stick with finding a sub t first to possibly use that here. So now our r of t was given, but we need v of t. So we need r prime of t. So v of t, which of course is r prime of t, equals negative 4/5 sine of t, and then negative cosine of t, and then our last one is 3/5 sine t. So now we have our velocity, and we need the magnitude of velocity. We could find the acceleration now and then find that dot product. But if we find the magnitude first, then we can pick whichever one of these is the easier route to go. We can either take the derivative of the magnitude, or if that looks like it's going to be a mess, then we could take the dot, find acceleration, take that dot product and do it that way. So the magnitude of v of t equals the square root of, can I fit this here? I'm going to go to the next line just in case I can't fit it there. Equals the square root of, so the 4/5, we're going to get 16 over 25 squared times sine squared of t. 16 over 25 sine squared t, and then plus cosine squared of t, and then plus 9 over 25 sine squared t, which was nice of them. This is going to sum to 1 sine squared t. So this is sine squared t plus cosine squared t underneath the square root is what that simplifies to, which is just 1. So it's the square root of 1. So we just get this equals 1. Which equals 1. So now in our choice of formulas, we could either take the derivative of 1, or we could find the derivative of this and take its dot product with v dot with a, and then divide by 1. It's much easier, of course, to take the derivative of 1, so we're going to go that route. So a sub t. If you wanted to, you could check the other route and find acceleration, do the dot product, and in that scenario, that instance, you would those two things are clearly must be perpendicular in this scenario, because we know we're going to get 0 this route, which means we would have to get 0 going that route as well. All right, so a sub t equals the derivative with respect to t of 1, which is 0. So there's our a sub t. Now we need to find the normal component of acceleration. So we have the option of using this formula or that formula. If we use this formula right here, we still have to find acceleration, find its magnitude. We don't have to square it. We would usually have to square it. We're not going to have to square it this time because that thing is 0. So the square root and the square will cancel one another out. The other alternative is to find acceleration, do the cross product of acceleration with this velocity, and then divide by the magnitude of velocity. Since we already went one easy route, I'll go this is easier, hands down in this problem. And most of the time, this is the easier route. So you can try that one. I'm going to go this route just so we can see the steps of doing it that way as well. All right, so, but yeah, if I were just doing this problem, just trying to get the job done, I absolutely, for this problem, would go that route. And 9 times out of 10, I probably would go that route versus this route. All right, so now we need acceleration. We can still see the formula we're using. So a of t, or b prime of t, or r double prime of t, whatever you want to look at it as. So b prime of t. So now I'm going to take the derivative of this vector right here that we had, and we're going to get -4/5 cosine t, and then we're going to get negative sine t, so we're going to get sine t, and then we're going to get 3/5 cosine t. And I'm doing this so that I can use this formula again. So now I need to do v cross a, and let's see, can I fit that down here? And then I need to take the magnitude of that. I already have the magnitude of v is 1. So v cross a, where is my v? So my v is here. I'm going to cross this with this vector. I am going to get -3/5 cosine squared t for my minus, I'm going to need a little space for this, -3/5 cosine squared t, then minus 3/5 sine squared t. That's my first component. Second component is going to be -12 over 25 cosine t sine t, and then minus a -12 over 25. Sorry. Yeah, minus the negative 12 over 25 cosine t sine t, and the negative of that, but it's 0. So we just get 0 right there. And if you're computing this cross product, don't do like me and sit here and do it in your head. Go off to the side and work it out. But since we're not working on cross products anymore, you're all familiar with that. That's why I'm not doing the steps explicitly here on the paper. And then lastly, our k component is negative 4/5 sine squared t, and then minus 4/5 cosine squared t. So negative 4/5. What did I say? Which one was first? Sine squared t. And then minus 4/5 cosine squared t. All right, so there's a comma right there, sorry. So our I component, our j component, our k component. And now we have our cross product. Now we need to find the magnitude of the cross product. Of course, this reduces, and this just ends up being negative 3/5, that term. And this is just negative 4/5. So let's go ahead and simplify that first before we find the magnitude. So this equals the vector negative 3/5, comma, 0, comma, negative 4/5. And we need to find the magnitude of this. So the magnitude of V cross A, which is just going to be equal to the square root of 9 over 25 plus 16 over 25. 9 plus 16 over 25, which gives us 1. So now we have what we need to use this formula. We got the numerator is 1. We already had the denominator is 1 somewhere right here. So we have the denominator is 1. So a sub n, the normal component of acceleration, is just 1. I'll go to the next page. I didn't want to, but so a sub n, which was the magnitude of V cross A divided by the magnitude of V, is just equal to 1 over 1, which of course is 1. And had you used the other formula, you would have gotten the same thing. You would have gotten 1 that way. All right, next we are going to look at number 22. And so we're on the next page. We're on page 795 now. Number 22 says, show that the curves parameterized by R1 of t and R2 of t, and I'll write down what those are, intersect at the point 0, 1, 0, and that the vectors tangent to the two curves at 0, 1, 0 are parallel. All right, so they give us R1 of t is the vector whose first component is 1/2 t squared plus t. So 1/2 t squared plus t. Second component is t plus 1. And the last component is negative t. Then R sub 2 of t is equal to the vector whose first component is sine of t. Then second component is e to the t, and then negative tangent of t. I forgot what we were supposed to do. Show that these two curves intersect at the point 0, 1, 0, and that the vectors tangent to the two curves at 0, 1, 0 are parallel. So first we're going to show that they intersect at 0, 1, 0. That means we need to find some value t for which this is equal to 0, 1, 0, and this is equal to 0, 1, 0. Now, the values of t, where they occur, and like on the homework, if I gave you all something like, when I gave you all something like this on the homework, I will put s as the parameter in one and t as the parameter in the other one, just because you can have two curves intersect at the same point, but they don't get there at the same time. Say, for instance, curve 1, it starts at t equals 0 and goes to t equals 50. At time t equals 3, it might be a 0, 1, 0. Where curve 2, it might start at time t equals 0 and go to t equals 1,000,000. And it might be at time t equals 70, it's at 0, 1, 0. So they can hit the same place at different times. So the t that I get for this need not be the same t that I get for that to hit that particular point. So that's why I tend to use a different parameter. I use s for one and t for the other one. So because if we solve for t here, the automatic assumption is that we use that same t here. That's not always the case. Now, it may or may not be the case for this problem, so we'll see in a second. If it is the same, if these hit that point at the same time, they clearly both are going to hit that point because that's what the problem is telling us. But are they going to get there at the same time? We don't know. And the problem didn't really ask us that either. So they're telling us to show that this thing at some point is 0, 1, 0, as well as this one at some point is 0, 1, 0. So it could be we had to jump through a bunch of hoops, or to solve here. Like you could say, okay, well, I'm going to take this first one, set it equal to 0 and solve for t. The t's, whatever you get for this one is going to be the same whether you use that component, or that component. So easiest component here to use is the third component. Third component tells us t equals 0. You could use this one, set that equal to 0. It's just a little bit harder. And then down here, same thing. You pick whichever one you want to. If you want to set negative tangent of t to equal to 0 and solve it that way, that's fine. Or e to the t equal to 1 and solve it that way, that's fine. It doesn't matter. So let's look at R1. So for R1, I'm just going to use the k component, negative t equals 0. And let's just make sure that that gives us what we want for the other components. If t equals, well, let's just first write it. So t equals 0. I'm going to call it t1 because it corresponds to R1. Looks like the t is equal to 0 for that one too, but they still could have two different times they could hit there. So let's just make sure though that at t equals 0 that all of these correspond. So that of course gives us 0 because that's what we use to solve. Put t equals 0 here, we get 1. Put t equals 0 here, we get 0. So that works out. Now for R2, pick whichever one you want to use. I'm going to use e to the t equals 1. You can use sine of t equals 0. Did they give us some bounds for this problem? They did not. Yeah, so I wouldn't use sine of t equals 0 because sine is periodic and there are infinite many values for which sine of t equals 0. But we would need, so even if you use that one, you would then be forced to go and look at one of these other ones as well because you wouldn't know what value of t actually is the correct one that we need. So we're going to use e to the t. So e to the t equals 1. So t2, this would also be equal to 0. And we'll double check sine of 0 is equal to 0. Tangent of 0 to sine over cosine of 0. E to the 0 is 1. All right, so that works out. So we know that the two lines do indeed intersect at the point 0, 1, 0. Now they asked us to find, and the vectors tangent to the curves at 0, 1, 0 are parallel. So now the vector tangent to the curve, remember, is going to be your velocity vector or your derivative of your position vector. So r1 prime of t equals, so here we're going to get just t plus 1, and then here we're just going to get 1, and then here we're going to get negative 1, and we're going to end up plugging in 0 for this because we're trying to make sure that they're parallel at that point. So first let's find r2 prime is equal to cosine of t. So we're taking the derivative of this one now. So we get cosine of t, we get e to the t, and then we get negative secant squared of t. So notice these two vectors, there is no scalar by which you can multiply that vector and get this vector right here. So in general, they're not parallel to one another. But what we're looking at is we're looking at t equals 0 because we plug in those values. Are the two parallel at that particular time? So r1 prime of 0, we put 0 in here, we get 1, 1, negative 1, and then r2 prime, we put 0 in there. Remember, had we gotten two different values, we would be putting in two different values, but we just happen to get the same value here. We put that in, and cosine of 0 gives us 1, e to the 0 gives us 1 as well, and then secant squared of t. So remember, secant is 1 over cosine, and cosine of 0 is 1, so we just get negative 1 because this is negative, the negative of 1 over cosine squared. So it's just going to give us negative 1, and these two vectors are clearly parallel to one another, which is what they were asking us to show. All right, so that concludes section 12.5, and our next lecture video will be, because we don't cover section 12.6 or section 12.7, so our next lecture video will be section 13.1, but that won't be until Monday's lecture since we have a test on Friday this week.